Hello students in organic chemistry. This is going to be the first of my YouTube videos for preparing you for chem activities. This is for chem activity 2 to be performed on Wednesday, September 26th. Before we get started, I'd like to talk a little bit about why guided inquiry is worthwhile, why I do it, why I have you buy the books and spend your class time doing it. Most people don't necessarily like guided inquiry. They're not necessarily comfortable with working in groups. They would rather just have a passive learning experience. But as you can see from this chart, people only learn small amounts or remember small amounts of what they read, see, or hear. A very good lecture might provide lots of opportunities to see and hear, in which case the passive learning is still happening and a person might be able to use some of that material again, but only 50% of what they see and hear matters. It's also well known that people tune out after about 8 or 9 minutes of a lecture unless there's some interactivity. However, with active learning, you can learn much more and retain much more and use it in much more creative ways than you can with passive learning. This model of learning is a result of many years of study and education. Specifically, why we use process-oriented guided learning, it works very well for science courses, content-heavy courses. In general, guided inquiry facilitates learning higher grades. People at the top of the scale are probably going to earn their A's anyway, but this guided inquiry has been shown and proved again and again to help the people who are struggling more than the people at the very top. Guided inquiry also leads to greater retention of material. I've seen it in my own students. In our chemistry major courses, we give comprehensive exams 1 or 2 or 3 years after we complete a course, and the courses that I've used guided inquiry as one of the teaching methods, those students have done better on the comprehensive exams than students before that time. It's a good use of class time. Why should I spend my class just telling you what you can go learn from reading or web tutorials and so on? You should use the class time to actually learn where your misconceptions are and how to do things better. It leads to a more thorough understanding of the material. It's not just a bunch of facts that you write down and then regurgitate. You actually have to use the material to answer the questions. And possibly most importantly, it builds group dynamics. It builds a support system within the classroom. It helps you learn to work in a group. These soft skills are things that employers in every field need. Working in teams is part of the modern world. So, in order to make your chem activity most useful during the class period, there are certain things we need to keep in mind. First and foremost is respect. I expect everybody to respect each other, to respect me, and I will do the same for you. It's important to treat each person and their ideas with the appropriate respect. You need to assign someone as a group manager, and each time you meet you can pick a different person for this role, but the group manager will kind of keep people focused and keep the conversations from wandering away or the progress from slowing. Everyone in the group should have a workbook or a photocopy of the chem activity so that they can read the reading sections and then discuss the problems properly. And everyone should attempt to write down the answers as we go. You should, in a given class period, work quickly through the easier material. There's no reason to spend time if you already all know. But you should, however, stop and address each person's questions and make sure everybody understands. Finally, I will provide clicker questions to help keep you on track. Okay, the second part of this video is going to be a brief review of Lewis structures and formal charges to prepare you for doing this yourself. And I picked the carbonate ion C2H3O2- as my example. Now when you do Lewis structures, you have to consider how many atoms you have and how many valence electrons there are on each atom. So for example, carbon has 4 valence electrons and there are 2 carbon atoms. There are 3 hydrogen atoms, and each of them has 1 valence electron. And there are 2 oxygen atoms, each of which has 6 valence electrons. And finally, because there's a -1 charge, there's 1 extra electron. Okay? -1 charge means an excess of electron charge by 1. Now when we go to make Lewis structures, we need to share electrons in order to make the second row elements have octets, and the first row elements, like hydrogens, have duets, or a total of 8 or 2 valence electrons around them. They can have these valence electrons from the electrons they originally have as atoms, and by sharing those electrons. In organic chemistry, normally the carbons are bound together. So we can start by drawing the 2 carbon atoms next to each other. One carbon atom brings 1 electron, the other carbon atom brings 1 electron, and together they share a pair of electrons to make a bond. Each of those carbons also has 3 additional valence electrons that is not involved in this sharing. Now there are several possible ways to draw a correct Lewis structure from this formula. I'm going to concentrate on the one that equals carbonate. The one that equals carbonate has both oxygen atoms attached to the same carbon atom. So one of the oxygen atoms would share one of its unpaired electrons with carbon, like so. The other oxygen atom could share a second unpaired electron with an oxygen atom, like so, with 5 that it still has for itself. And this is the basis of our molecule. We still have hydrogen atoms to put in. Hydrogens, because they can only form one bond, always end up on the outside or the ends of chains. So let's start putting in those hydrogens to fill in everyone's valence. This carbon has an unshared electron. It can share that electron with one of hydrogen's electrons to make a carbon-hydrogen single bond. It can do that again. It can do that again. And now the carbon atom on the left has a total of 2, 4, 6, 8 valence electrons. And it has an octet. Each of these hydrogens has a duet. But we're not done. First off, we still have an oxygen that's got a single electron, an oxygen with a single electron, a carbon with a single electron. We have no more hydrogen atoms to make bonds with. At this point, when we have extra bonding sites and no more external atoms to put in, we start talking about multiple bonds. So imagine the electron down here, 1 electron from carbon and 1 electron from oxygen forming a second bond, and that would make the net double bond between carbon and oxygen. Okay? So now this carbon has 2, 4, 6, 8 valence electrons, and all we're left with is this oxygen, which is hanging out here with 7. But wait, we've got 1 electron left over. That's our extra electron that went with our negative charge, and that extra electron could sit right here. Now the oxygen on the outside, 2, 4, 6, 8. The oxygen that's double bonded, 2, 4, 6, 8, and everyone's happy. Now the normal bonding state of carbon is for carbon to have 4 bonds, and for oxygen to have 2 bonds, 2 lone pairs. I'm going to redraw the structure in the more classic form, in which a pair of electrons is replaced with a bond, like so. So the CH bond here, that line means a pair of electrons. This line means a pair of electrons. This line means a pair of electrons. Now we draw the carbon atom on the right. This line means a pair of electrons between the 2 carbon atoms. Single bond to this oxygen. Double bond to this oxygen. 2 extra pairs of electrons. There's your 8. 2 bonds, 2 lone pairs. And then this one had 1 bond and a total of 3 pairs of unshared electrons. Okay? So this carbon atom has 4 bonds as expected. This carbon atom has 4 bonds as expected by valence theory. This oxygen atom has 2 bonds, 2 lone pairs as expected by valence theory, but this oxygen's kind of unusual. The last oxygen does indeed have an octet, but it does it in a non-standard way. It does it by having a total of 1, 2, 3, 4, 5, 6 electrons that aren't part of a bond, and then a 7th electron, if you think about it, sharing electrons with carbon. So total, for bookkeeping purposes, it has 7 valence electrons. Okay? Well, oxygen normally has only 6 valence electrons. So this oxygen atom actually has an extra electron. So we give it a formal charge of -1. Formal charges are ways to keep track of where any excess or deficiency of electrons is in the molecule by assigning it to a specific atom that either has an excess or deficiency of electrons. So now we have a Lewis structure for the carbonate ion.